Good morning. We are now discussing few concepts of astrophysics. Astrophysics is the branch of physics which deals with the physical properties of heavenly bodies such as stars, galaxies, the planets, the solar system, and so on. So, among the physical properties, we usually study the mass, the dimensions, the density, the volume, and the distances of these heavenly bodies from the earth. So in this, we first concentrate on a concept called parallax. This parallax is defined as the difference in the apparent position of an object when viewed by the same object along two different lines of sight. As an example, if we observe certain object with both eyes open, and if the same object is observed from the left eye, that is by closing the right eye, and vice versa, that is by observing the same object with right eye by closing left eye, we can observe the shift in the position of the object. And this shift is not real, it is apparent, and therefore we say that it is the apparent shift in the position of the object when the same object is viewed along two different lines of sight. And this we call it as the parallax. And this parallax is measured by the angle, or otherwise known as semi-vertical angle, inclined between those two lines of sight. So you can see here from figure, this is the angle, and this angle is called the parallax. And here we have the object. A certain star is considered as an object. The star or object is observed from two different lines of sight. Let us take this as A and this is as B. From two lines of sight, the object is observed, and this is the center of these two objects. And from that center, if we draw a perpendicular line, and the angle made by this perpendicular line with one of the line of sight is called the parallax. And that angle we call it as the semi-angle or semi-vertical angle of inclination. Nearby objects will have larger parallax, in the sense larger angle of inclination, and very distant objects will have the smaller angle of inclination, otherwise known as smaller parallax. And hence, this parallax is therefore used to determine the distances of the objects which are very far away, just by measuring the angle subtended. So coming to the heliocentric parallax. Helio meaning sun, centric meaning center, sun being at the center of this parallax measurements. The parallax of a celestial object, that is heavenly body, by using 2 points on the Earth's orbit around the sun being at the center of the orbit, and this type of measurement we call it as the heliocentric parallax. Measuring the distance of a very distant object such as star or planet, or a heavenly object from the Earth's surface, or from the Earth's orbit around the sun. We are measuring the distance of heavenly object from the Earth's surface when Earth is revolving around the sun, and this is called the heliocentric parallax. Or otherwise, it is the shift in the apparent position of a star as observed from the Earth on opposite sides of its orbit, and it is therefore called heliocentric parallax, or otherwise known as stellar parallax. We can also define it as the parallax obtained with a baseline of 1 astronomical unit. The baseline of 1 astronomical unit is nothing but the distance between the Sun and the Earth. This is Sun. The distance between Sun and Earth, this distance is called 1 astronomical unit. 1 astronomical unit, 1 AU. Distance between Sun and Earth is 1 AU. That is, the baseline is equal to 1 astronomical unit. Then the parallax obtained with the baseline of 1 astronomical unit is called heliocentric parallax. And this is true only if we measure the angles from the Earth's surface when the Earth is revolving around the Earth, when the Earth is revolving around the Sun. And this parallax can be used to measure distances up to 300 parsec. 300 parsec. So here you can see we are measuring the angle of a star from the Earth's surface when the Earth is at the extreme left end of the orbit, Earth's orbit around the Sun. Similarly, we have measured the same star, or we have measured, or we have photographed, or we have observed the same star after 6 months when the Earth is on the other side of the Sun in its orbit. So you can see here the baseline is represented here as 1 AU, distance between the Earth and the Sun. So when the baseline is 1 AU, and this will happen only if we measure the position of the star from the Earth's surface when the Earth is at its two extreme ends of the orbit around the Sun. In the background of fainter stars. The background of fainter stars. So as in this case, first is it was observed in the month of January. So you can see how it is in the month of January. Similar observations are made in the month of July, that is after 6 months. So you can see the stars. You can see the star behind the fainter stars. There is a slight change in the background stars which is negligible. So now coming to certain definitions regarding the astrophysics. One such definition is the parsec, and these are the units used to measure distances related to astrophysics or heavenly bodies. One parsec is defined as the distance at which the star will have a parallax of 1 second of an arc. If the parallax is equal to 1 second of an arc, then the distance of that star is called 1 parsec. Then the distance of that star from the Earth, if that star makes an angle of 1 second of an arc, parallax is nothing but the angle, the semi-angle or the semi-vertical angle. If the star makes a semi-angle of 1 second of an arc with the Earth, then the distance of that star from the Earth is said to be equal to 1 parsec. 1 parsec. And 1 parsec will be equal to 3.26 light years. 3.26 light years. So coming to the astronomical unit. It is the distance between the Sun and the Earth. The distance between Sun and the Earth is called 1 astronomical unit, and that distance will be equal to 1.5 into 10 power 8 kilometer, or 1.5 into 10 power 11 meter. Astronomical unit is abbreviated as AU. Light year is defined as the distance traveled by the light in one complete year. And 1 light year is equal to 9.5 into 10 power 12 kilometer, or that will be equal to 63,300 astronomical units. 1 light year is equal to 365.25 days. 365.25 days, it is 1 year. 1 year multiplied by 24 days, multiplied by 24 hours into 60 minutes into 60 seconds, and multiply this with the speed of light, which is approximately 3 into 10 power 8 meter per second. 3 into 10 power 8 meter per second, and this approximately gives 9.5 into 10 power 12 kilometer, or otherwise 9.5 into 10 power 15 meter into 15 meter, and that will be nearly equal to 63,300 astronomical units. It is 63,300 times the distance between Sun and Earth, and that will be equal to 1 light year. We know that 1 PC is equal to 3.263 light years, and therefore if you convert this into the astronomical unit, 63,300 multiplied by 3.263 gives 206,265 astronomical units. It is 1 PC, 1 parsec is equal to 206,265 times the distance between Sun and the Earth, or that will be equal to 3.085 into 10 power 16 meter, or 3.085 into 10 power 13 kilometer. This is about the units used to measure the large distances that we come across in astrophysics. So now coming to stellar parallax. Stellar parallax is a measure of distance of the star from the Earth. Stellar parallax is defined as the angle that 2 in the arcsecond subtended by the star with the mean radius of the Earth's orbit round the Sun. We have considered the star as sigma. Sigma is our star under consideration. And if this star makes an angle P, that too in the arcsecond, then this angle made by the star with the Earth's orbit, with the radius of the Earth's orbit around the Sun, then that angle we call it as the stellar parallax. Nearby star sigma is considered, and it is photographed from the Earth's surface when Earth is at position A against the fainter background stars, fainter far off background stars. Similar observations are made after 6 months when the Earth is at the exact opposite end. That is, when the Earth is at E dash. From these observations, the total angle is measured, that gives to P, and half of that is P, and comparing the change in position of star during 6 months with reference to the fainter background stars whose shift in position due to the motion of the Earth is negligible. Now, the parallax measured in this way is called the trigonometric parallax or heliocentric parallax or annual parallax, since the parallax is measured only once in a year. Therefore, it is called the annual parallax. From the above figure, we have tan P is equal to opposite by adjacent. So, opposite by hypotenuse, tan theta. Tan theta is opposite by hypotenuse. That is tan P equals A by D. tan P is equal to A by D. Since P is very small, therefore tan P become equal to P, therefore P equal to A by D in radian, where D is the distance of the star from the Earth and A is the distance between the Earth and the Sun. 1 radian is equal to 206.265 seconds of an arc. Therefore, parallax in seconds of an arc is P by 206.265, that is equal to A by D, or D equals 206.265 A by P in parsec. Now therefore, since P is expressed in seconds of an arc, radius of Earth's orbit is 15 into 10 power 10 meter, and if 206.265 A is taken as unit distance, that is 1 AU, or 206.265 A is taken as unit distance, that is 1 PC, then D become equal to 1 by P. The unit of distance is called parsec. The unit of this distance is parsec, and we know that 1 PC is 206.265 astronomical unit, or 3.263 light year, or simply 3.085 into 10 power 16 meter, or 3.085 into 10 power 13 kilometer. Now, the reciprocal of parallax in seconds of an arc is the distance of the star in parsec. So 1 parsec is the distance at which radius of Earth's orbit subtends an angle of 1 second at the star. 1 parsec is the distance at which radius of Earth's orbit makes an angle of 1 second of an arc with that of the far off star. So coming to apparent brightness. The apparent brightness of a star is defined as the total energy received from the star per unit area per unit time at the Earth's surface. It is the total amount of energy received by the Earth's surface per second per unit area, and that we call it as the apparent brightness. For the Sun, if the star under consideration is the Sun, then the total amount of energy received from the Sun per second per unit area is called as solar constant. The apparent brightness in the case of Sun is called solar constant. The apparent brightness of a star can also be defined as the total energy received from the star to its surface area. Thank you.